Hello everyone, welcome to Code Enzyme. This is the 16th video of the series Graph Algorithms for Competitive Programming. And in this video, we will discuss the strongly connected components. First of all, sorry for the late video because I was busy with my mid-semester exams, so I was not able to continue this. So basically, in this video, we will discuss this problem from the CSES problem set. That is the flight routes check. Okay. Uh, and we will discuss what strongly connected components are and how to actually go about it. Okay. Now, first of all, I want to give you some definitions so you can understand what strongly connected components actually are. And there is a tagline for this. So this is the tagline for this. So whenever, if you ever see this line, like every node can be visited from, so every node can be visited from every other node. That means it is talking about strongly connected components, and this is only asked for the directed graphs. So no one talks about strongly connected components and the undirected graphs. Okay. So now that you know this, let's move on to the some definitions. Okay, so what are strongly connected components? Basically, if you are given some graph, so if in a component every node can be visited from every other node, it is a strongly connected component. Okay, so this is the basic definition in a layman language. Like if you in a component, every node can be visited from every other node in that component. So there should be in that component. That component is strongly connected component. So that is the short form. Now, as an example, let's say you have some graph, like it is a directed graph, obviously. So is this a strongly connected component? No, right? Because I can visit 2 from 1, but I can't visit 1 from 2. Now, the counter example will be like if I have 1, 2, and we have something like this. So is this a strongly connected component? You will say yes, because I can visit 2 from 1 and then 1 from 2 again. Okay. Let's say if we have, what if we have something like 1, 2, and 3, and this is so is this a strongly connected component? No, right? Because I can't visit 1 from 3, right? I can visit 3 from 1, 2 from 3 from 2, but I can't visit 1 from 3, right? And the count so the counter will be like just reverse this edge or maybe add one more edge like that. So if there is a cycle in the directed graph, then this is forming a strongly connected component. Now I can visit every node in this component. I can visit every node from every other node, basically, right? So now that you know what strongly connected components are, let's also discuss one more thing. Like let's say we have something like 1, 2, 3, and 4. So this is basically a strongly connected component. What if I add more edges? Is this a strongly connected component? You will say yes. So basically, if we add more edges, the if we so basically if we add more edges, the component is still strongly connected component. Okay, so we can add more edges, but we can't so we can add more edges and we don't have to worry about it. Okay, now there are basically two algorithms that are used for the strongly connected are used for finding the strongly connected components, and you can even make your own algorithms, but the most popular ones are these two. One is called the Kosaraju algorithm, and the other is called the what should I say? And the other is called the Tarjan's algorithms. I might make some spelling errors, but the names that I remember are these. Okay. And in this video, I will only discuss the Kosaraju algorithm, and I will give you a feel for Tarjan's algorithm also, like how it is working. But this Tarjan's algorithm is also using the concept of DFS low linking. So it is not something that I have discussed in this playlist right now. So I am planning to cover this in the later part of the playlist right now. So I will only focus on the Kosaraju algorithm for now. Okay. So first we will see how Kosaraju algorithm finds the strongly connected component, and I will give you a feel for it how we are actually doing it. Like, okay, so now I am discussing the Kosaraju algorithm. Okay, if you want to find the strongly connected components in directed graph, let's consider a graph. So let's say the starting vertex is this. Okay, and now let's say there is one more edge to this one, then we have something like 3, then we have 4, something like this. Let's say we have 5, 6, 7, and this. So what are the strongly connected component in this whole graph? I can say, like, okay, this one is a separate strongly connected component, this one is a separate strongly connected component, these three are separate strongly connected components, and these three are separate strongly connected components, right? Because if you see, I can't visit one from any of these strongly connected components, right? I can't visit two from any of the other strongly connected component. No, no, sorry. I can't go in reverse order. Basically, I can't visit in both directions, right? So that is why these are separate strongly connected components. Okay. There might be more edges like this also, but that doesn't change the fact. So how can we actually go about it? Go about finding this? So the idea is, if I so there are two ideas to actually find the strongly connected component using the Kosaraju algorithms. I will give you the two ideas. First idea. So the first idea is, if the component is strongly connected, then if I maintain a reverse graph, if I reverse all the edges, I will still be able to visit all nodes in the component, right? So that is the first idea, that if you reverse all the edges, then you will still be able to visit all the nodes. So let's also consider the reverse graph of this whole graph. So we have 1, then we have a reverse edge, 2, then we have something like 3, then we have 4, then we have uh, like this, and then like this, 5, 7, then 6, and then up. Okay, so in this graph also there are the same strongly connected components. This is the strongly connected component, this is the strongly connected component, and this is the strongly connected component. And one thing that you will realize is the order of traversal really matters. Okay, even in this graph, like if in this graph I am starting from 2, let's say I am running a DFS, so I will say, like, okay, 1 is visited, then 2 is visited, then 3 is visited, and if I go for 4, then I might encounter a cycle and I will say, okay, I might have found a strongly connected component. But in DFS, we don't actually choose it by ourselves. So it might happen that I will enter some other strongly connected component by mistake, right? So what I can do is, let's say I start my DFS from node 1. Okay. So I'm starting my DFS from node 1, and now like I saw that node 1 was unvisited. Now I will now I will do my DFS in the reverse graph. Okay, so in the reverse graph, from 1 I can't go to any other vertex, so I will say my DFS ended. So 1 is a separate strongly connected component. Okay, I might be going a bit too fast, so you can actually reverse the video a couple of minutes and try to rewatch it. Okay, then I will go to 1, and then, like, 1 is visited, then I will go to 2, and then I will traverse in the reverse graph and visit all the nodes that I can. So 2 is visited, 4 is visited, 3 visited, so all these are visited. Notice that now if the graph is reversed, I will not enter this strongly connected component, right? So that is the idea of Kosaraju algorithm. Whenever you are at an index which is not visited, you now run the DFS in the reverse order, in the reverse graph. Okay. Okay, so now that you know the basic idea, your question should be, will this always work if I start from any node, right? So let me just actually give you a counter example. It won't actually work if you start from any of the nodes. So let me make a graph. So we have something like 1, 2, 3. Let's also make a reverse graph. So we have 1. Okay. So if you start from any of the node, let's say you are starting from node 3. Okay. So you will say, okay, let's mark visit at 3, and now I will visit all the nodes that I can visit from 3. So you will say, okay, this is visited. But what might happen is you might also visit 1, right? And now if you will visit 1, you will say this whole thing is a strongly connected component, which is wrong, right? You should have visited 1 and said that 1 is already a separate strongly connected component from this graph, and you will realize that you can't actually visit 1 from this in the original graph. So so your approach is actually wrong. You can't actually start from any of the node that you want. So what should be the correct traversal order? Okay, so if you want the correct traversal order, let's say you want to start from node 3. Um, Basically, so there is a concept called back edges. How should I actually? So to understand this, why it is not working, need to understand what back edges are. So let's say you have something like this. Okay, so in the DFS tree, when you are traversing the a graph, let's say you have something like this. So you visit one node, then you visit another node. Okay, then you visit another node. Okay, so in the DFS, you did something like this, and then you have some edge that is pointing in the reverse direction. Like when you have strongly connected component, there will be an edge that is pointing to the backside, right? In the to one of its ancestors that was already visited, right? So if you have something like this, then like okay, so if there is a back edge, like if you are at the if you are at the lowest level and you have a back edge only till here, then clearly this is a separate strongly connected component, because from this node you can't go above this, right? But let's say your back edge looks something like this. So now this whole thing is a strongly connected component, because not because it is forming a cycle. This is the up value, that how much, like if I'm starting from this node, I can go up, like how much I can go up. So this is using the concept of DFS low linking. How much can you go up if you are at somewhere down? I know I'm not able to explain it actually properly right now, but you don't actually need to understand why this is working. But okay, this is one of the ideas I will discuss in one of the further videos in the playlist. But for now, you need to understand that okay, how the idea is forming for the strongly connected components. And basically, when you have this, what node should you start your traversal from? Okay, let's actually try to form a DFS. We saw that from 3 it was not working, right? So let's actually try to form the DFS tree. So what will the DFS tree look like? So if I'm at 3, uh, let's try to form the DFS tree. So from 3 I can visit 5, right? Then I can visit 6. Then I can visit 4. Then I can visit 2. Right? Now 1 is a separate thing. I can't visit 1 in any case. Yeah. And you will realize that there is a baggage from 6 to sorry, there is I can also visit 7. So there is a baggage from 7 to 5. There is a baggage from 2 to 3. Yeah. And then we have 1. So since the n degree of 3 is not 0, I should visit 1 first. Okay. So the topological sort of this whole thing is like 1. Then we have 3. Then I can take any of these like 3, 5, 6, 7. Okay. No, there is a baggage for 5, so I can't take actually like this. So the topological sort looks something like 1, 3, 1 3 4 2, okay, 1 3 4 2, then we have 5 6 7. So in this order only you should do your DFS in the reverse graph. So what we will do is let's first visit 1 because it is first in the order, and I will mark this as visited. And now I can't actually go in any of the in any other component. So one of the strongly connected component is 1, okay. Then I will go to the next node, that is 3, and so 1 is visited, and now I will mark all the nodes that I can visit from 3 which are not visited. So I'll mark like in the reverse graph. So 3 is visited, 4 is visited. Now from 3 I can go from 3 2, and now I will not go to 1 because it was already visited. So 4 is now visited. Now all these nodes are visited, if you see, okay. So this will tell me that okay, now these three are visited and they are a separate strongly connected component. So let's say 3 4 and 2, okay. Now I will reach 5. So I will say okay, now let's say so now next node is 5. So because these are already visited, so DFS will skip it. So let's say now I am at 5, and I will mark the 5 as visited, and in the reverse graph I will check like I want to visit all the nodes that are visited, right? So I will say okay, uh, which are not visited. So I will say okay, 5 7 and 6 are visited now, and these are a separate strongly connected component. So 5 7 and 6. So that is the idea of strongly connected components. And one thing and the only thing that I think I have missed is what are condensed graphs. So condensed graphs. So let's say you have a very big graph, something like 1 2 3 4 5, and then we have 5 6 7 and this. So if you have something like this, you can make a condensed graph out of this, because this whole thing is one strongly connected component. So you can say like 1 and then 2 and then let's say 5. So what I'm doing is I am representing this whole component by this single element, okay. So I will have to maintain like in the strongly component that one is a part of, I will say the part are 2, sorry, only one is there in that. So I can maintain some sort of adjacency list like that, or I can say DSUs kind of thing that will also work. So in this 2 I have 2 3 and 4, and in this 5 I have 5 6 and 7. So we have three strongly connected components, and these are the nodes that are part of those components, okay. So this is called the condensed graph. So I don't think I was able to explain it properly, but I think if you actually so I would suggest you to watch it slowly, and if there is some part that you do not understand, kindly comment down this video. So maybe I will be able to explain it in the later part of the playlist, okay. Now let's actually move on to the code. How do we actually code this up? So what is the input format? First of all, there are n cities and m flight connections. Your task is to check if you can travel from any city to any other city using the available flights. Now flights are only unidirectional, so this is the directed graph, and this is the tagline. If you can visit every node from every other node, then we are talking about some kind of strongly connected components. In the input, first of all, the first line has two integers n and m, the number of cities and the flights. So let's actually take it. So let's say we have n and m, c and n and m, okay. Then I think there are m edges. So let's say vector, uh, let's say vector int graph of n plus 1. And since we are using Kosaraju algorithm, I will also need to maintain a reverse graph. So let's say reverse, or I can call it r graph n plus 1, okay. Then for I in range m, let's say int uv, uv, c in u and v. I will say graph of u dot pushback v, and reverse graph of v dot pushback u. Okay, so I have this now. Now why why do I even need the graph? Because we want to find a topological sort. And why do we need the reverse graph? Because we want to traverse in the reverse graph to mark all the edges as visited. Now my first task is to find the topological sort. So I will say, let's say vector int of vector bool of visited of n plus 1 comma false. Initially every node is not visited, and now I will need the topological sort. So let's say topo. Let's make a function of int of void. This will be a void function. And so if you don't actually understand this, how to find a topological sort, you need to check the previous part of the playlist first and then come back here. Okay, so let's say we are here. First thing I will do is let's say visited of node equals to true, and then I will traverse in all the children. So graph of node, and I can say what if not visited of child, I will say dfs of child. And once this is done, I will say topo dot pushback pushback node. And now I will have to go for every node. If not visited I will say okay dfs I. So this will give me the topological sort in reverse order. I will have to reverse it. So reverse what? Topo dot begin comma topo dot end. Okay. So now I have this. Let's actually debug the what are we actually getting. So we have, let's try to debug the topological sort. So just so I know that it is working. So the topological sort is 1, 2, 3, 4. 1 should come before 2. 2 should come before 3. 3 should come before 1. Uh, Actually this is a package, so we don't actually, so it might happen. Obviously the topological sort will not exist for a strongly connected component because it is a cycle. But uh, at least we got a DFS tree. We don't want to find the topological sort basically, but we want to find the DFS tree. Uh, they both actually achieve the same purpose. So you can actually try to find the topological sort also. So we have the topological sort. Basically, we did find the DFS tree of the directed graph, and now I will make another function which is very similar to this function. Let's actually call this DFS2, and this time I will traverse in the reverse graph, and let's also call this DFS2. And let's actually set everything visited of I equals to false. After this, I will say for I in range 1 if not visited I. Actually, let's say a vector int strongly connected component. So this will, I will maintain a list of the strongly connected component, the parent of the condensed graph. Like in this case that we discussed the condensed graph, whenever I have some unvisited node, I will say mark the parent. So now I can say sc dot pushback. So pushback I, and then I can say dfs2 of I. I don't need to do this anymore, and this I need to do in the order of topological sort. So in topo, let's actually debug the SCCs that I am getting. So you will see I am getting two strongly connected components. One is 1 and another is 4. Let me just draw this test case to see. First we have 1 and 2. First we have a node between 1 and 2, one edge like this. Then we have 2 and 3. So let's say 2 and 3. Then we have 3 and 1. Okay, so this is another strongly connected component. Then we have 1, 4. So 1 is pointing to 4. And then we have 3, 4. Okay. So what you will realize that 4 is a separate strongly connected component, and 1, 2 and 3 is separate strongly connected component, and now there is no route to travel from 4 to any of this component, right? So that is why we are getting two components, and I think this is the correct answer. So now I can say if scc dot size is greater than 1, then I will see out no, because there are more components. Now I can see out SEC 0 because I need to print any two cities which cannot be visited. So SEC of 1 with an handle. In the else case, I can simply see out yes. Let's run this and we are getting the correct answers. Let's actually submit this quickly. Is there any debug statements that I missed? Okay, I think I missed the debug somewhere. Let's actually try to run this. Okay, so it is running and now let's try to submit this quickly. So we have flight routes check. Okay, why is it giving wrong answers? Because I'm printing 7 and 1. I should print 1 and 7. Okay, so it might happen that I think I will just make it 1 and 0. Yeah, I think because I was traversing in the reverse graph, it might happen that I'm not able to visit the first. I will be able to visit first one and the second one, but I will not be able to visit from 1 to 0 like that. So that is why it is giving me wrong answers. Let's actually submit it again. Make sure that I saved the file and run this again. So now I think this should work. Yeah, so our solution got accepted and I hope you were able to understand it. Um, if you have any doubts, you can comment down and tell me if you like the white background better or the black background that I was using till now. And so let's continue the series further. Thank you for watching if you have watched till here. Really appreciate it. And I will see you guys next time. Thank you.